Hey everybody, it is me, Steve, and this is going to be my last video before we start preparing for our ISS transit this weekend. What you are looking at here is just a generic cross-section of the interior of the Earth that I grabbed off of the internet. The link is in the lower right there if you want to look at it. It's an okay representation. It's not the greatest, but actually it's pretty good. I actually have gone into a lot greater detail on how we know what we know about the interior of the Earth in a Geo-Rant. I will link it below, so you can go look at it if you want. But anyway, what are we doing here today? Well, we are going to try to figure out, there are basically 8 main layers, if you will, to the Earth. I hate using that word. And we are going to compute the volume relative to the entire Earth that they take up in percentages ultimately. What you are looking here is just a cross-section through the Earth. It's as if you cut the Earth in half. It doesn't matter where you cut it in half. Just cut it in half. It's not oriented any particular way. It doesn't need to be. But here I am showing you basic parts of the interior of the Earth here. And as you can see off the legend here, we have average depth range in kilometers, and then in parentheses, the numbers in parentheses are the thickness, and the bold numbers are the actual percentages, and I'm going to walk you through how I calculated these to 1/10 of a decimal place. And I noticed here that there's an error. Yeah, there is. The transition zone, it says transition zone, but it doesn't have the actual thickness. That was an oversight on my... Oh, wait, yeah, it does. It's slightly to the right of the up and down line. My bad. Didn't need to correct myself, and I did. All right. Now, obviously, the interior of the Earth is not a simple layer, onion-type situation. We know this. I am going to represent it as one for simplicity purposes. This diagram here is kind of more or less how a more realistic view of it. You can see here these black arrows show convection lines. The orange part here is what is called the D layer. This layer, although I modeled it as kind of an onion layer, it actually has a lot of topography on it, and it rests. It's the transition between the mantle and the outer core, and in some places it's 200 kilometers thick. In other places it's almost 0, and it has this weird dynamic to it. It's kind of a very unique layer. But these red areas are magma chambers rising up through the mantle. What you see, these here are lithospheric plates descending into the mantle through subduction, and the squiggly lines on top are just the crust. I didn't include those as separate layers. I basically just picked the discontinuity boundaries. I'm not going to go through and name them here. I've done that before. I'm just going to draw the boundaries, because even though the lithospheric slabs are descending into the mesosphere, at what point do those lithospheric slabs and mantle become indistinguishable? Because eventually they're going to be reincorporated into the mantle through heat and pressure. Is it a 1 kilometer gradient? Is it a 100 kilometer gradient? We really don't know the answer to these questions. So I just decided to ultimately go with the onion layer model. All right. Now here's the basic structure of the Earth's interior. You can read this stuff if you want. I'm not going to go through it in detail, but there are 8 basic divisions I'm working with to compute the volume. So just read those if you want. And basic volume calculations of the Earth's interior. At the end of the video, I'm going to have all my references like I always do, and I'm going to show you the raw calculations I did on paper. I'm not going to go through every single one of them here with you, because this video would be way too long. But basically here we have the crust, or CR. It's what I did for this is I had to figure out an average thickness for the crust, because like all these other layers, their thickness does vary to some degree, and the crust and the lithosphere probably have the greatest thickness variation. So I just basically took the average of the oceanic and continental crusts, which is 40 kilometers. The lithosphere, same thing. The oceanic continental crust lithospheres and the crust included, which I will separate out when I run the calculations. So as you can see, I got 125 kilometers average from the top of the crust to the base of the lithosphere. And then the asthenosphere, transitional zone, mesosphere, D-layer, outer core, and inner core. These are taken basically from my references. Some contradict a little. Some layers are not as well known, so I just had to approximate the best I can from those other sources, like especially the outer core, inner core boundary. I've seen depth ranges ranging from 51 to 5200 kilometers, so I picked 5150, in that case too. But this will still give us a general idea of the relative volumes of these units. In order to calculate out volume, we need to calculate the volume for each sphere or layer and subtract the volume from the underlying sphere. What I mean for that is when we run this calculation for the inner core, I have to calculate the volume of a sphere. For the outer core, I have to calculate the volume from the top of the outer core down to the center of the Earth. For the D layer, from the top of the D layer down to the center of the Earth, and then I subtract the underlying unit from that. So I subtract the underlying sphere from that in order to get the volume of the unit that I want. The volume for the inner core is the simplest equation because you don't need to subtract anything because it's at the center. It's just the way it is. I don't need to subtract anything because there's no underlying sphere there. All you need to do is calculate its volume. First, let's calculate the total volume of the Earth. The equation for the volume of a sphere is right there. Volume equals 4/3 times pi over r cubed. And at the bottom is the actual calculation for the total volume of the Earth in cubic kilometers, which is what I'm going to be working with because they're smaller units. And as you can see, that's to the 12th power. So they're pretty big units as they are in scientific notation. So I'm going to walk you through the math for the inner core and the outer core only. And I did this for all the units all the way up to the crust, okay? So basically, to figure out the volume of the inner core, I need to know the radius of the Earth, which I took, that's 6,371.01. That's the radius of the average radius of the Earth given by NASA on their fact sheet page, all right? So I just went, it's actually 6,371.008. I just rounded it to 0.1. All right, so we take that radius, we subtract the depth in kilometers to the core, and there's actually a few different ways you can do this, but this is the simplest way. And we get 1,221.01 kilometers, which becomes our radius. So then we just plug that into the standard sphere volume equation, and we get the volume of the inner core at 7.62511 times 10 to the 9th cubic kilometers. From this point on, I'm just going to drop the units. After that, you're just going to see the numbers. So in the next line here, what we do is we take the volume of the inner core and divide it by the total volume of the Earth, and we get a number. We multiply that by 100 to get a percent, which is approximately 0.074%, which I ultimately will round to just 0.7, because that 0.074 is I mean, it's an accurate number, but it's not it's a precise number, but it's not an accurate number. That's something else I've also talked about, accuracy versus precision. Although that's a very precise number, it probably doesn't reflect reality that much. The margin of error on all these is probably plus or minus 3 to 5%. But they're a lot better than some of the estimates I've seen online. All right, the outer core, same thing. Radius of the Earth minus the depth to the top of the outer core, we get a number. That's our radius. We compute the volume, our OCV, subscript V, which is our volume of the outer core. We plug that into this bottom equation where we just divide it by the volume of the Earth like we did in the inner core. We get a number which we multiply by 100 to get our percent. All right. But now, the inner core volume we didn't have to do anything with. That 0.7% is the number we're going to use. But the outer core, well, we have the inner core in it, so we have to subtract the volume of the inner core. So to get our OCV, we take 16.297 minus 0.704, which equals, I left the dot off the 15, but it's 15.3593%, which is approximately 15.6%. Okay? And like I said, a tenth of a decimal place is where I'm going to carry all these numbers to. All right, so the layers of the Earth, here they are. Run through all the calculations. These are the layers of the Earth in percent volume. All right, your inner core, outer core, D layer, mesosphere, transitional zone, asthenosphere, lithosphere, and crust. You add them all up. I get 100, so my math is right. It's a way to check yourself. Now, sometimes the inner and outer core are just referred to as the core, and if you add those percents together, you get 16.3% is the volume relative to Earth. So the core itself makes up 16.3% of the Earth's volume. And then we have the lower mantle, which is 55.7. And then these three layers here, the transitional zone, asthenosphere, and lithosphere are all technically what people refer to as the upper mantle. That's 26.9%. You add those two together, you get 82.6%. So I've seen other averages that give the volume of the mantle anywhere from 80 to 86% volume, but this 82.6 is probably a lot more accurate of a number. And the crust stands out on its own because when most people are introduced to the layers of the Earth, they're basically introduced to the crust, the mantle, and the core. So, and as you can see, the crust is only 1.1%, and the inner core is 0.7. So they're both, if you average in the full percent, they're both 1%. But if you remember in the slice of the Earth I showed you, the inner core in my circle looked a lot bigger than the crusted, which is this thin skin. That's because we're not working with a circle. We're working with a sphere. And although the crust is a lot thinner than the inner core, it's spread over a much larger area. Well, the entire surface of the planet, as where the core is just at the center. So that's why on diagrams, the inner core looks so big, but it's actually a very small volume percentage of the Earth as a whole. So I hope that quick little introduction of how to do volumes served you could understand my ramblings there a little bit. Here's my references. Now, in a later video, I'm going to use these volumes to compute mass percentages relative to the Earth, where the mass of the Earth will equal 100%. So there is some sort of somewhere I'm going with this. Plus, it's just kind of cool once in a while to figure this kind of stuff out. But anyway, that is it. If you have any comments or questions, please leave them below, and I hope you learned something.